In the first lecture, we talk about exoplanets. We'll talk about the definition of a planet and the definition of an exoplanet. We'll look at the history and discovery of exoplanets and the rapid growth in their numbers in the last few decades. And we'll finally look at the exoplanet characteristics that are being measured by large telescopes on the ground and in space. Carl Sagan long ago said, "I don't want to believe, I want to know." Many people are aware that Carl Sagan is a giant of astronomy, one of the first great popularizers of the subject, and he was also one of the founders of the field of astrobiology. He set the bar very high for the discovery of life in the universe. One of the things he said was, extraordinary claims require extraordinary evidence. In this course, we're going to look at the ways that life might be found beyond the Earth. And those claims will be subject to that very high bar that Carl Sagan set decades ago. Meanwhile, his quote reminds us that believing something is not the same as knowing it. We must apply the scientific method. People have speculated about the existence of planets beyond the solar system and the existence of life in the universe for centuries, actually for millennia, since the start of science. But only in the recent past, in our own lifetimes, have we had the tools and the capabilities to answer the question, are we alone in the universe? Let's start with our situation in cosmic space. We sit on an average middleweight planet. There are planets smaller and larger than ours in the solar system, orbiting a middle-aged, middleweight star, the Sun, about 5 billion years old. The Sun itself orbits a middle outer region of the Milky Way galaxy, a spiral galaxy that consists of hundreds of billions of stars. The Milky Way galaxy itself is typical of spiral galaxies elsewhere in the universe. The Milky Way is part of a cluster of galaxies called the Local Group. By this point, we've reached out in the universe millions of light years. But we can go further, and in the end, we'll find hundreds, millions, and even billions of spiral galaxies. So whatever we deduce about our situation in time and space, and the presence of planets near us in the Milky Way, and the potential for life on those planets, we can expect to extrapolate to the much larger universe beyond. Let's look at the definition of planets. A planet is a solid or partially liquid body orbiting a star, but it's too small to generate energy by nuclear reactions. All the planets in the solar system are essentially rocky bodies surrounded by gaseous envelopes. In the case of the terrestrial planets, the gaseous envelope is quite slender. The Earth's atmosphere is no thicker than the skin of an apple compared to the size of an apple. While the giant planets have small, super-Earth-sized cores and much larger amounts of hydrogen and helium. But they all fit the definition of being much less massive than the star they orbit. For example, in the solar system, if you swept together all the planets, plus all their moons and the asteroids and the comets thrown in for good measure, it would amount to less than 0.1% of the mass of the Sun. So planets essentially are rocky debris left over from the formation of a star, and they constitute a tiny fraction of that star's mass. In astronomical terms, they are small bodies in the universe. By being so small, they cannot have nuclear reactions. The only heat they have is heat generated internally by radioactive decay in the rocky material, or perhaps the heat that they get from their parent star. But they do not generate their own radiation or light. When we see planets, whether they're planets in our solar system or the exoplanets we are now discovering far beyond the Earth, we see those in the reflected light of their parent star. The IAU, the International Astronomical Union, decided to define what a planet was because astronomers were starting to find objects smaller than Pluto that appeared to be at the boundary between moons and planets and asteroids, and so people were starting to get confused. This definition says that a planet is a celestial body that is in orbit around the Sun, has sufficient mass for its self-gravity to overcome rigid forces so that it assumes what is called hydrostatic equilibrium, meaning it becomes nearly round in shape, and has cleared its neighborhood around the orbit. Let's look at these in a little more detail. Being in orbit around the Sun or a star is pretty easy to understand. The size of the planet dictates its shape. because as planets form, the material is not exactly solid. The rock is hot and viscous and can flow. So when rocky objects are small enough, they don't actually have to be spherical. The twin moons of Mars, Phobos and Deimos, are potato-shaped, and asteroids are also elongated. So these are not spherical objects, and they're too small to be planets. The third part of the definition was a little controversial at the time, and it's part of the reason that Pluto was demoted from the pantheon of planets in the solar system. It says that a planet must clear its neighborhood of material. So the planets orbit in circular or near circular orbits around the star, and when they form, they sweep up the material that becomes their mass. If an object has insufficient mass, it's not able to sweep out the material around it in its orbit, or it fails to meet the definition of a planet. What then is the definition of an exoplanet? You may also see this referred to as an extrasolar planet, meaning being beyond the sun. An exoplanet is simply a planet orbiting a star that is not the sun. As I mentioned, people have speculated about their existence for centuries, but until 1995, we knew of no planets orbiting any other star than the sun. So this is an entirely new field of astronomy, barely 30 years old. People have speculated about the existence of planets and life beyond the Earth and beyond the solar system for centuries. One of the visionaries in this field was Giordano Bruno, who declared in the late 16th century, "This space we declare to be infinite. In it are an infinity of worlds of the same kind as our own." Bruno actually went further and speculated that on some of those worlds there might be living creatures of diverse forms, some similar to the Earth and some dissimilar to the Earth. This is a shockingly modern idea to be espousing before even the invention of the telescope. But this was definitely a notion not accepted by the culture or the church of the time, because just after the Copernican revolution, the idea that the Earth was not the center of the universe and humans were not the pinnacle of creation was a radical idea. Newton's universal law of gravity is the primary tool for understanding orbits in the universe, and it's the primary tool for diagnosing the existence of an exoplanet around a distant star. Because until very recently, we were unable to see the exoplanets directly. So we see them indirectly by their gravitational effect on their parent star. And we use Newton's theory of gravity to do this. And he's quoted as saying, "And if the fixed stars are centers of similar systems, they will all be constructed according to a similar design and to the dominion of one." The history of discovery of exoplanets is very interesting, because actually the first discovery, which tends to be forgotten even by some astronomers, was of a small exoplanet, barely Earth-sized, orbiting a pulsar. Now, a pulsar is a dead star formed from the collapse of a massive star. Such a star is a remnant of a star, has no radiation, is not emitting light. But it was very unprecedented to imagine a planet around something exotic like a pulsar. This discovery in 1992 essentially got buried in the science literature. Nobody knew what to make of it, and it didn't seem like a classic exoplanet, an Earth-like planet orbiting a sun-like star, so people essentially forgot about it. But I guess when Nobel Prizes are awarded, as they probably will be for the discovery of exoplanets, attention should be given to the group that found the first planet in 1992 around a pulsar. But to the history books, the field genuinely starts in 1995 with the confirmation of the first exoplanet around a living star, a sun-like star, still emitting radiation. But even this exoplanet was very unusual. 51 Peg, as it's called, had very big surprises for astronomers. First of all, the orbit, 4.4 days. Think about that. Mercury is the closest planet to the Sun, orbiting in slightly under 3 months. And so here was a planet orbiting in less than a week around its parent star. By Kepler's law, it was very close to its parent star. And so it was incredibly hot. There was no hint that this might be a habitable planet. It was a large planet too, about half the mass of Jupiter. And it was a surprise to the astronomers who discovered it. They had not set off on a search for exoplanets. They were working on binary stars. and the object was in their search list because they anticipated it might be part of a binary star system. So they were surprised instead when the star, 51 Peg, was being tugged around by an unseen and fairly massive companion. This discovery was done with a 1-meter telescope in Switzerland. So this was a surprise because this first exoplanet was in a position that completely alien to our experience of the solar system. A massive planet extremely close to its parent star, and really nobody knew what to make of it. But it was exciting because it was the birth of a new field of astronomy. In the next decade or so, exoplanets started to be discovered by the same technique. As we'll discuss later, the method used for these first discoveries was the Doppler method, where the exoplanet is not observed directly, it's too faint to be seen, but the exoplanet tugs on its parent star, and the tugging induces a wobble in the parent star, which manifests into a Doppler shift of the star's light. This exquisite technique was really what allowed exoplanets to be discovered for the first time in the mid-1990s, after decades of searching. The next landmark, after a slow increase in the number of exoplanets, was the launch of the Kepler spacecraft and the Kepler telescope. The Kepler mission advanced our knowledge of exoplanets enormously, as we'll see. In particular, it is able and was able to discover Earth-like planets, and some even smaller than the Earth. Literally thousands of exoplanets are now known, most of these from the Kepler spacecraft. In this graph, we can see the candidates as of June 2010, showing how the number of planets had evolved. And you can see that most of the orbits of these planets are also rapid. Much like 51 Peg, they're orbital periods of days, weeks, or even a few months. Really nothing like the Earth. But of course, that's what took time, because as we see on the right-hand side, as the amount of data has increased through to last year, we're starting to fill in the distribution out to orbital periods of hundreds of days or several years. Also, the number of planets growing at small sizes and small masses has increased because Kepler has the sensitivity and precision to find objects like the Earth or even smaller. This horizontal line represents the size of the Earth, this represents the size of Neptune, and this represents the size of Jupiter. The very first exoplanet discovered would sit here in this diagram, 51 Peg. So you can see that it's a very large planet with a very fast orbital period. But now Kepler is finding objects much like the Earth. Objects that are the size of the Earth or even smaller, and objects that have the Earth's orbital period or even larger. And so, as we speak, the number of exoplanets confirmed has skyrocketed to nearly 4,000. In this animation, we see the crescendo of discovery of exoplanets starting in the last 20 years. Historically, 5 planets seen to the naked eye, going back to prehistoric times. We're looking at logarithmic period of the planet orbit and logarithmic mass in Earth masses. By the end of the 19th century, still just a handful of planets. The final planet, Pluto, discovered early in the 20th century and later demoted by astronomers to the status of dwarf planets. Through this period of time, people are looking hard for exoplanets, but none is discovered. In 1995, the first discovery, and then the acceleration. Initially by the spectroscopic method, looking at the Doppler shift, and then finally with the launch of the Kepler satellite using the transit or eclipse method. Look at the rate of discovery changing. And at the end, Earth-like planets. Another view of this progress shows the discovery as a function of mass over time since the first exoplanet. And here we can see that the mass limit of the lowest mass planet has marched downward. Remember, this is a logarithmic plot. Linear in time, logarithmic in mass. And so that means that the discovery detection limit of mass has grown exponentially, or got better exponentially over time, over 2 decades. That's an extraordinary success. In astronomy, usually you're limited by the size of your collecting area of your telescope or the amount of time you can gather data on a particular object. So to make gains of this magnitude, orders of magnitude in mass, is extremely difficult. In this case, it's done entirely by instrumental precision, by exquisitely accurate spectrographs measuring the spectra of parent stars to look for the very subtle Doppler wobble. The Doppler wobble is the method used for the first 100 or so exoplanets, and as I mentioned, the Kepler spacecraft then took over and has produced most of the discoveries since then. The Kepler spacecraft looks for a different signature of an exoplanet, the subtle transit or eclipse. When it crosses the face of the star, we see a slight dip in the star's brightness. This dip repeats periodically with the same period as the orbital period of the planet, and that's the signature that Kepler has used to find all of its planets. So this combination of methods, the Doppler technique looking for the wobble indirectly, and the transit or eclipse method used by Kepler, watching a slight dimming of the parent star, these together have found most of the exoplanets we know of. And in rare cases, and very valuably, we use both techniques on the same object, which gives us extra information. This is another way of looking at the distribution of exoplanets, and especially the first exoplanets to be found. We're looking here at their distance from the parent star, and here's the model of the solar system with Mercury, Venus, Earth, Mars, and Jupiter. And you can see the surprise that astronomers experienced when many of the first exoplanets found were what are called hot Jupiters. These Jupiter mass or similar to Jupiter mass planets orbiting extremely close to their stars, far closer than Jupiter orbits the Sun. So even as exoplanets were discovered, confirming a speculation of astronomy from centuries ago, there were surprises and puzzlement among astronomers. How could exoplanets form so close to their stars? One of the characteristics that's important to measure when an exoplanet is discovered is the eccentricity of the orbit. So we define eccentricity in astronomy as the amount by which the path of an orbiting object deviates from a perfect circle. When an eccentricity is 0, it's a perfectly circular orbit, and an eccentricity of 1 indicates a highly elliptical orbit. In our solar system, most of the planets have low levels of eccentricity. The Earth's eccentricity is about 5%. Mars has about 20% eccentricity. So these are slightly squashed circles. In fact, if you looked at a map of the Earth's orbit, the eye would be hard-pressed to detect the deviation from a circle. So we've seen that one of the surprises of the early exoplanets was the fact that they were massive planets, Jupiter-like, on very close, tight, rapid orbits of their stars. The second surprise was that the eccentricities of most of the early exoplanets were much larger than the eccentricities of most planets in the solar system. And that trend has continued. In this diagram, we show a few hundred of the first exoplanets. We could put more on a diagram, but it gets so busy it's hard to read. And you can see by the squashed circles that most of them have eccentricities that are significant, 10, 20, 30, 40%. Jupiter's orbit is shown for comparison, very nearly circular. And so this became a second puzzle in the emerging exoplanet field. Why were the orbits of so many of the exoplanets so eccentric compared to the orbits of planets in the solar system? And again, raised a second issue of whether the solar system was typical. Now, lurking behind this is something called the Copernican principle. The Copernican principle, stemming from the Copernican revolution, is that we have no privileged place in the universe. There's nothing special about our situation. And everything in the history of astronomy has affirmed this after the Copernican revolution. Copernicus showed that the Earth is not the center of the universe, and since then, in the modern era of astronomy, we've shown that the Sun is not the center of the Milky Way is not the center of the universe, and there's nothing special about our situation in cosmic space. And yet here, we had early indications in the field of exoplanets that our solar system was not typical of these new discoveries. Here's another way of making that clear. Here's the orbital eccentricity as a function of the orbital distance. And you can see the planets of the solar system near the bottom of the diagram, so small eccentricities, nearly circular orbits, and here's their distance from the sun on a logarithmic scale. And again, you see how many exoplanets have much larger eccentricities, much more elliptical orbits. So let's summarize what we've learned in this lecture. We've learned how astronomers define a planet. A planet is a solid rocky object orbiting a star, like the sun. It is massive enough to form a spherical shape, and it's also massive enough to clear out its region around the star. This is the definition of the planets in the solar system, and it's also applied to exoplanets. But exoplanets are planets orbiting stars other than the sun. We've seen that the first exoplanet was discovered in 1995, and it was a surprise. It was a very massive Jupiter-like planet orbiting very close to its parent star and orbiting faster than a week in an orbital period. But since then, hundreds and now thousands of exoplanets have been discovered, and the smallest and lowest mass of these rival the Earth in size and mass. Thousands of exoplanets are now known. And these exoplanet orbits, in large part, make us wonder if the solar system is typical, because many exoplanets have been found that are closer to their stars and more massive than the terrestrial planets, and many exoplanets have been found that are on more eccentric orbits than any of the planets in our solar system.